Thanks for joining us. And we often talk about the Space Nuts shop, which is on our website, spacenutspodcast.com or spacenuts.io, whatever you like. Look what turned up. If you're a YouTube viewer of Space Nuts, you get a big advantage right at this moment because I can show you these. The new Space Nuts stickers and the logo designed by my brother Steve, who came up with that great slogan of ours, science, space and stuff. So there they are. But, you can find them on our website. We've got a link to the Space Nuts shop there if you're interested. Now, Fred, let's move on to this next topic. And it is all about brown dwarf stars. Now, we know of about a couple of thousand of them in our galaxy, but they think there might be more and more because they've found one that's different, and that could open the way to there being more and more and more of these things that we didn't know about. And from what I understand, this one was quite an accidental discovery, which also Indeed. Correlates to the name of it.
That's right. Yes, I love the name. Its proper name is WISE-A J153429.75 minus 104303.3.
Say that 10 times fast.
But they nicknamed it the accident, and I like that very much. We haven't really talked much about brown dwarfs on Space Nuts,
Not much.
Which is a pity. One of my former colleagues, Chris Tinney, who's now at the University of New South Wales, was one of the pioneering pioneers of brown dwarf studies. Really interesting objects, and in a sense, they sit between gas giant planets like Jupiter and stars like the Sun in their mass range. So they're sometimes called failed stars because, although we do define them as brown dwarf stars, but it's because they don't have the nuclear fusion that generates all the energy at the center of a star like the Sun. That nuclear fusion kicks off because the temperature of the cloud of gas that is about to form the Sun is increased to 10 or 15 million degrees by the compression of the gas. So you need a lot of gravity to produce that compression, and that switches on the nuclear fusion, and then you've got a star. If you have a cloud of gas that collapses but doesn't have enough mass to raise the pressure and hence the temperature to that critical, 10 or 15 million degrees or whatever it is, then you get something which is smaller and has some features of a star, but isn't a star, and that's what's called a brown dwarf.
Right. And
the features that they have is that they do emit energy at a very low level, and in fact, they're called brown because they radiate most of their energy in the infrared region of the spectrum, the redder than red light.
Yep.
So they were. Even though they were hypothesized actually a long time ago, they were only really discovered when infrared astronomy came of age in the 1970s. So now, as you mentioned, we know of a couple of thousand of them. So they're sort of intermediate between planets and stars. They probably have weather, a bit like planets do, but they do radiate energy a bit like stars do. And it's not the fusion of hydrogen which is causing that radiation. It's something called deuterium burning. It's a low-level nuclear process that is enough to keep the star warm, but not to make it hot. So when you're looking for brown dwarfs, what you do is you look for stars that are sort of faint in some wave bands. For example, a brown dwarf, the light of a brown dwarf star contains virtually no blue light. Yeah. So if you're looking for an object that's radiating the blue, you're not going to find a brown dwarf. But once you move your wave band up to the infrared, they get brighter, and it's because they're cool. So cold objects, you know this from just thinking about red hot metals and white hot metals. When a metal's white hot, it's very hot.
Yeah.
But as it cools, it goes redder, and it just goes redder and redder, and eventually you can only see it in the infrared spectrum. The same is true with stars. So infrared stars that are cool, you detect by their infrared radiation.
Otherwise known as Fonzie stars.
That's a very accurate description, yes. Okay. Which confuses things now, but never mind. We'll move on, because the thing about the accident, and the star that's called the accident, is that it's got the right sort of brightness in the wave bands that suggest that it's very cold. In other words, in the infrared there, so it's kind of, well, it's faint in the visible spectrum, put it that way.
Yep.
So there's just nothing there. But when you look at certain of the other wave bands, and what we're now doing is dividing infrared up into slices. And in fact, we do that. We call it near infrared, mid-infrared, far infrared. These are all well-known technical terms in the trade. Some of those wave bands, it's actually brighter than you'd expect it to be. And that's a puzzle. So it's giving you a mixed message. It's saying, in one wave band, it's saying, oh yeah, I'm cold, I'm a genuine regular brown dwarf. But in other wave bands, it's saying, no, I'm actually quite hot and bright. There's something interesting here. And so the people who do the physics of this sort of thing have thought about it long and hard, and have kind of worked out why this should be. The bottom line is that this star, the accident, is an extremely old star. So it was formed when the gases from which stars are formed was not as rich in heavier elements as it is in more recent times. You and I have spoken before about how the amount of iron in a star spectrum is an indicator of its age. Stars with virtually no iron are very, very old, because they were formed from gas that was really just hydrogen and helium. There wasn't anything else. But as time goes on and stars themselves generate the iron and then come to an end, spread that among in the interstellar medium, so that new stars form with much more iron. That's what we call the enrichment of the interstellar medium. It's how these elements appear. So the thinking now is that the accident actually formed at a time when, first of all, there was less carbon than there is now, or than there was more recently. Because the carbon is one of the sort of indicators that suggest it's brighter in this region of the spectrum than it should be. If it had more carbon, it would be fainter in that region. And so what they're saying is, yes, this is a star that formed from the primordial mix, not quite primordial. It would have had some heavier elements in it, so it wouldn't be part of the first generation of stars, but dates back to the early years of the universe, perhaps 13 or so billion years ago. So it's a very, very old star. And they now suggest that there might be a whole population of these things that have been missed because they've got this peculiar response in their different wave bands.
Yeah, fascinating. It's also moving rather fast.
Yes, it is. That's correct. It's whizzing round. Let me do the calculation in my head. It's several hundred kilometers per second, about 800,000 kilometers per hour. So you divide it by 3,600, which I'm doing in my head, and getting about 200 kilometers per second, I think, is the
wow,
roughly, very roughly.
That's moving along. It's not far away either, 50 light years.
Yeah, it's quite close. That's right. So whizzing by. So yes, a really interesting object that might open the way to studies of a whole new population of these weird brown dwarfs, accidental brown dwarfs.
Yes, indeed. And I just received a note from the Department of Political Correctness. We're not allowed to call them brown dwarfs anymore. We have to call them stars with disabilities. So
yes,
sorry about that.
Confusing two different sorts of dwarfs, I think. Yeah.
Maybe.
Yes.
Just insulted dwarfs. Sorry about that.
No, I don't think we have. No.
Okay. You're listening to Space Nuts with Andrew Dunkley and astronomer at large, Fred Watson.
Space Nuts.
You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.